which is trends in GIS employment. And so if we go on to the next slide, see that we have some information here. The information that I've drawn here, and then I'm gonna ask both Barry and Steve to join in a discussion about this. But the information I've drawn here is about the jobs of geographic information system technicians, and then the next slide we'll see in a minute is remote sensing science and technicians, scientists and technicians. And this information comes from the Department of Labor from a system called ONET, which was last updated in 2019. So it's quite up-to-date information. And what they do with this database, the way they create it is they survey occupational experts, folks who've held these jobs for some time, folks who are involved in hiring, and they get their ideas about both, what's involved in these occupations and also what kind of training is needed for these occupations. And of course, today we have Barry here, so this is going to be fantastic in terms of he's somebody who's involved in hiring and really knows the terrain very well in terms of the kinds of tasks that people are doing, the kinds of training that they need. So this slide here is about, as I said, about geographic information system technicians, so it's a little broader. So we can see this, managing GIS databases is an important part of this, identifying spatial relationships. Obviously, making really good quality maps is still an important part of this job. It's not something that computers can do automatically to really tell a story with a map and figure out how to tell a story beautifully. And then obviously modeling and analysis and data manipulation, these are all important parts of this profession with a median salary now of about $90,000 a year. So sort of captures that. And then the next slide, we have remote sensing scientists and technologists. And so managing remotely sensed data to obtain meaningful results, working across platforms for analysis of the imagery data and other forms of remotely sensed data, using both aerial and satellite imagery now. So we see now much more often, of course, the use of unmanned aerial vehicles, and we've begun to incorporate that in our Catalina Island course. And then just the ability to integrate other geospatial data into projects. So this is where that broadening aspects, for example, in the electives in our remote sensing curriculum, I think would be key in our remote sensing for Earth observation certificate, for example. So what I wanted to do is really ask Barry to give us some examples of maybe kind of what's going on in these tasks today, and maybe give us a bit of a reality check about whether this is up to date and captures the trends you see in what folks are doing in the industry.
No, there we go. Okay, now we can hear me. Why don't you go back to the other slide for a moment? We'll start there. So most people become aware of the data when it is already what we call from the satellite side in the can. And most of the jobs are accordingly in that zone. So let's just start there. The things that Bob said are very important. The nature of the relationship between classical maps and imaging information gathered by sensors is changing as computers take a larger role in correlating data. It used to be that you had pictures and you had maps and they were physically separate and quite frankly emotionally separate. Even in the industry, there were separate organizations that dealt with these parts of the problems and very rarely interacted with one another. But where we are now, the capability of large GIS engines, such as the Esri capability mentioned earlier, allow for users who understand what they're doing to take and correlate information from dozens of different kinds of applications and understand things that are not intuitively obvious from looking at them from the outside. Relationships between objects. If you're looking at a picture taken by a normal camera and then take something like, if you guys have ever seen those ghost shows, they're all looking at infrared cameras all the time to try and find ghosties. Well, objects look very different when you look at them in the infrared. And if you're looking at shots from a long ways away of each of the two types of information, it's not intuitively obvious that you're looking at the same thing all the time. Spatial relationships are similar, but they change, and understand how to correlate them and learn that the temperature of something, which is what you see in the IR information, relates in some sense to the health status of the visual object. For example, a full fuel tank is a different color in heat than an empty fuel tank. Starts to let you understand things about the objects. Data quality is very important. With these sources of information, you have everything these days from handheld cell phone images, to things being taken by very large, very well-positioned satellites. And understanding what they're actually telling you involves a lot of being able to extract the information and location out of that data. And that is the data manipulation task, trying to understand how to take the features and make them relate to one another. So let's pop over to the other slide for a second. So how do you get this information? Again, I mentioned a minute ago that it extends all the way from a satellite that you have to put in the picture looking down. I believe that's a Russian human-occupied satellite. And they actually do take handheld photographs out of those things and always have. But then all the way down to the cell phones we were talking about a few minutes ago. And understanding how to correlate that information and productize it is the role of the folks at the back end we were looking at. Creating sensors that will capture the information you actually need is the role of the remote sensing folks. Images are limited in what they can gather by how much area you have to collect and how much resolution you have to have, and creating the requirements for, and then building and then operating the satellites and airplanes and ground stations and other things that collect the data are all challenging and interesting jobs, where it is very critical that you understand first what the data is going to be used for, and then work backwards into how it can be collected most efficiently. Steve, you want to throw in on top of that with some thoughts?
Sure, Barry. So, some thoughts that we have, as Barry and I had this conversation recently about what, traditionally, probably 10, 15 years ago, was considered remote sensing. Today, the way we collect or acquire data is actually very different. The term we came up with that I think like even better is this idea of foraging data. So if you think of maybe those words, remote sensing has, if you will, a very technical approach, and it's very directed. Sometimes it's very active, where you're actually going and trying to get something of specificity that you're specifically looking at. The idea of maybe acquiring has this idea that it may be there, but you're actually pushing a system possibly to get some of these things done. But the idea of foraging may be that it's already there and you're just kind of collecting it all up. So when we think about data today, it's geotagged, that has coordinate values from which we can introduce them to a GIS on the the middle end, where we're actually going to do some analysis and then finally produce products from it. Things like Twitter feeds or geotagged information about say a text file, or then obviously the things that we see that are geotagged that would be kind of in the more remote sensing space, like an image that someone collects on their smartphone. These are all different ways that we now see populating the front end of how we then go out and create the data from which we can do something with it that's geospatially referenced. So the requirements, therefore, are much greater, and the data sets are much bigger in order to be able to manage this wealth of information that talks about things that are going on in the earth. By extension, some of the programs that we're creating at USC recognize this and then accommodate the requirements for being able to teach that and put it into context in the classroom. So the programs that we're building now touch on all of these things that I discussed and Barry discussed about how we collect information in order to be able to do something with it, with inside of a GIS.
Great, thanks. So you guys, one thing I've been curious about is to the degree to which with these new forms of data, there's also a trend towards temporal analysis, and how that plays in here. So do you have some thoughts about the added element of time in these data and how that's?
Yeah, it's very obvious to anyone out there that information has a shorter and shorter threshold of freshness about it these days. It's very easy to be looking at 2-day-old news feeds and get information that no longer tells you what's really going on. So looking at where we are right now in the information space, a lot of those big traditional remote sensing things, before we get into the idea of the foraging Steve was talking about, the remote sensing collectors, the data gatherers, were working in very large batch modes. The first large satellites doing the collection, which is where a lot of the stereo mapping techniques that are used today came from, were large photographic birds that actually had to wait until somebody dumped a film canister onto the ground to process the data. So by definition, it was anywhere between a week and 6 weeks old when you got it the first time. This made the game of bait and switch for folks who knew we were collecting very easy, because they actually, that's kind of the reason why the Russians developed rail mobile missiles in the first place, is they would put the missiles in one place on Tuesday, and then while the satellite wasn't looking, move them to another location, you get another photograph, and you miss the count of numbers of missiles. Now, an hour doesn't go by where information isn't being updated by news feeds and cell phone feeds and Twitterati and such. So finding a way to incorporate that information and take advantage of the trends that the time value is telling you, it gets you much more towards the idea of understanding what people are doing and why, than just where they're doing it. And that gets into the human element of the process of information gathering.
Thanks. Yeah, I think that's absolutely. I mean, we see the software now is developing new, new modes of analyzing for different forms of temporal segmentation and so on, right? There's a lot of stuff you can figure out once you can associate time and space, right?
Yeah, and the scale is a critical thing. We're getting to the point now where we're starting to get meaningful maps of the whole planet in certain ways. So we can see that kind of information. But at the scale of, then you're dealing with things at the level of weather patterns changing and such. But when you're looking at something happening inside of a room, your time scale has to be much shorter. So matching up the temporal frequency of the data you're looking for with the answers to questions you're trying to obtain from the information is also a critical part of figuring out how to run these systems.
Yeah. I wonder too.
Yeah, so a few things there, and to kind of show you where maybe the technology is going and why it's important. So it's really the application, in many cases, are driving some of the requirements to collect the data with higher temporal resolution or with more timeliness. So, we could start maybe with the idea of a static location like your house. So this is a location of which you're interested in throughout the day. So when we talk about security cameras or the ability to answer the door from a distance, this is all information that's relevant in time to, in this case, an application or an action. Being able to answer the door from a distance, or being able to, change the temperature of a room, or possibly turn on a water system. These are all things that have relative meaning to time, based upon an event occurring, like someone knocking on the door, or a temperature, say, reaching a certain point outside to where you would say you'd want to turn on the watering system. But to the point of where the future is taking us, let's think about driverless vehicles, driverless cars. But the requirement then for temporal resolution of, say, a sensor to be able to give us information about a very dynamic system that's changing around what the car is trying to then move on, in this case, a road, is hugely important. It needs a very accurate, detailed map or image from which it can then take action. So once upon a time, collecting an image of a road, maybe with a weekly temporal resolution, might have been okay. But now we're talking about things that likely need to be updated daily or hourly, or in some cases by the minute. And so where are the sensors that are going to assist us in doing that? So some of them could come from possibly satellites. So we think about small sats doing certain things. We think about UAVs as a service versus just a commodity. So something now that's always up and providing information, in this case, real-time information. And then obviously a suite of maybe static sensors that may be in place across road networks that enable us to have this kind of information, which in this case enables the application of driverless cars. So a lot of what we're talking about the temporal resolution being improved, is being driven by many of the applications that we see in the future. What's going to happen 2, 3, 4 years from now that are going to require us to have these types of data inputs in order to be able to successfully navigate.
Great. I think so. This is a good transition, I think, to if we go forward 2 slides here, or 1 slide, sorry, 1 slide. We start to think about these kinds of really futuristic changes that Steve's addressing, and we begin to think about a very common question that I get from students who are coming to our programs is, what software do I need to learn to be employable? And I think Barry, you have some particular perspective on that, given Yeah, given that you've seen a lot of software change in your career for sure.
Yeah.
What's your so do you think this representation here is a good representation kind of what's required now in these different roles, and what kind of advice would you give to folks about career development this way?
Yeah, to begin with that last question first, this is absolutely a very descriptive list of where the state of the need is today for folks who are going to be practitioners in the community. Just to explain in context what Bob meant by I've seen a lot of these things, I actually began my undergraduate career, I believe, as Steve did also, with punch cards, Fortran programming on punch cards for machines. So we've seen a lot of evolution in that end of things. And most of what we do in GIS today wouldn't have even been conceivable back then. It wasn't until the 90s till we had vector cartoons and video games that these tools started to even be conceptualized. Where we are right now is the set of applications you see here, and I hope a lot of you who are looking at this recognize a number of these things. ArcGIS is sort of the Google Earth for people who know what they're doing in tool space for trying to work with geospatial information. SQL, the query language, is the database and manipulation tool. C and C++ and the scripted languages are how one actually develops new tools right now. But right now is a huge aspect of that. 5 years ago, the best programming, Java was still a relatively new thing in how it was being executed. Python didn't exist yet, and so these tools are continually evolving. So the one thing that is both interesting, challenging, and unfortunate for a practitioner in their career is you can reasonably expect to spend the next 20 years learning new tools all the time. There is never a point where that's going to slow down with the way things are evolving. The good side of it is, for the most part, these tools are integrating and aggregating information to make it easier to manipulate. The first versions of GIS several years ago, every type of image and map tool you needed actually ran separately from each other. And doing integration was more or less done in PowerPoint because there was no other way to make the information flow together. These days, these tools flow between one another in such a way that if I'm trying to understand, say, the analytical relationship between the color of an object, which is easily represented using spectral information from ENVI, and its location in space and time and velocity, which comes out nicely in some of the ArcGIS tools, they work across each other. So you can actually use the information and flow data back and forth to learn what's going on. So you're going to have to continue to study, but the applications will become more powerful over time as well.
Fantastic. Can we go to the next slide?
Hey Bob, can I jump in there real quick?
Absolutely, yeah.
Yeah, so there's a great quote out there from a gentleman named Alvin Toffler, and he talked about illiteracy in the 21st century. And the quote is, "The illiterate of the 21st century will not be those who can't read and write. It will be those who can't learn, unlearn, and learn again." And so to Barry's point, and it's not to say that what we've learned once upon a time was wrong. In fact, it was very much right because we were very successful with what we had learned and the tools we were using. But it is to say that the technology is changing quick enough to where if we don't keep up with the technology, we likely will be left behind. As a metaphor, one of the things I like to think about in this, for those that know a little bit about sports, the game of golf as an example. The swing that a player uses is not what's changing in many cases. It's the technology that's changing around them. So when you look at how far, say, someone can hit it or what a ball can do when they actually play the game, the technology often is changing, and then what they're having to do is just figure out how to use that technology to get the same end result. But the idea of how to play the game, maybe the strategies that are used and possibly the swing that is used, those things in many cases haven't changed too much. So when we think about education, if we can make ourselves good spatial thinkers with the given that technology is going to change around us, then we're actually in a very good spot, because the way we solve problems and the way we think spatially and the approaches that we take to it, which often is taught in the classroom, then the tool sets that are provided in front of us from year to year to year as time marches on, we will be just as successful 5 years ago as we are today, as we're going to be 5 years from now.
Yeah, I absolutely agree. I mean, where we win is if we know the fundamental principles and we can teach ourselves as the technologies change too. We teach the students how to teach themselves in the future. Can we have the next slide? Another way to look at this is to look at some of the job skill requirements that seem to be most common, and it's just interesting to me here how this is. We see communication at the top and interpersonal at the bottom, and then some of the more technical skills in the middle. Sort of a very, was calling this a geek sandwich. We talked about it earlier. Steve, how do you see these the job skills that are in demand in what we do at USC?
Yeah, I mean, I think what we try to do when we put students in a classroom environment is that we try to figure out how to take the technology and then some of the things that are in the middle, as Barry pointed out very accurately earlier, and that is the kind of the geeky stuff that's in the middle. How to communicate that and then work with that on the back end. There's a great quote out there by Ted Turner, who said when someone asked him how was he so successful, his comment was, early to bed, early to rise, work like heck, and advertise. And it's very interesting, the first three, hard work and taking on the challenges of the day and not being scared to get your hands dirty and those kinds of things, being efficient with your time, that maybe is what's in the first three, but then the last one is hugely important, and that is to be able to advertise or to communicate what it is that you've done. And usually that requires your ability to be good in groups, to have good interpersonal skills, and then be an effective communicator. So in the world that we're in, much of what we communicate is through visualization. And so when we think of geo-visualization, the final products on the back end, which traditionally were two-dimensional maps, now we've moved very rapidly beyond that. And so we're in 3D space. And if you include time, we're in 4D space, how things are changing and over time rapidly in 3D space. Being able to communicate that is what we believe to be one of the critical skills. So much of what we do in the classroom requires these types of presentations at the end of creating a product. So we use tools, obviously, Esri has a tool called StoryMap, which is a very impressive tool that allows you to communicate geospatial products to, in this case, a customer. And we try to integrate much of that into all of our classroom settings so the students are held accountable for this critical task of communication.
Yeah. I like this. I had heard from a dean at the engineering school many years ago that he was told by an employer that there was never an engineer who was fired for lack of technical skills, but lots who were let go for lack of communication at some point along the way. So we try, with the writing in our courses, and we actually have a writing instructor who works with our program, and all of the coursework we do, including the thesis on the GIST side on the MS GIST, we really do emphasize this ability to communicate the value of your work and communicate the structure of your work to others. It's important for being a team player. Barry, do you have any thoughts on this? Do you see this? Do you see programming rise? Do you think programming is going to rise up as a as a demand here?
That's an interesting question, because I think the answer is yes, but you have to be very careful what you mean by programming when you're looking forward. As I was saying earlier, and I think I could have said it better, but if you looked at the programming languages that were available when we started out, the code was very much at the level of making the computer do anything useful at all. It was numbers programmed up to then ASCII programmed up to then coding to make things work. And so you were manipulating the information not so much at the data level, but at the instruction level to do anything useful. Now we're at a level where the scripting languages that exist allow you in most applications to start with sort of a physical understanding of the objects, and code is just pulling blocks in. There are sensor models, for example, that you just pull a block that says optical filter and pull a block that says focal plane and such, and these things start to generate a lot of the information for you. At a gross level, those kind of tools on the remote sensing end are still going to require practitioners to build. The customization of these things is still going to be a feature at the geekiest end of the discipline. But really, the thing that struck me when I mentioned, and you commented on the geek sandwich type phrasing of this, is that most of the interesting information to me that is evolving these days in the GIS environment is at the point where you recognize how humans are relating to the environment. And that's why what Steve said about story maps is so important. The narrative of what's happening in a situation is what makes it interesting for almost all the applications. So I believe that the programming itself will become something more around trying to find ways to simplify the process of creating the story rather than manipulating the data. There is an interesting debate in the community about the relationship between two terms you hear all the time that are huge in the field: artificial intelligence and machine learning. For practical purposes, I differentiate those two things. Machine learning involves asking questions of data where you know what question you're asking, but don't know how. There's just too much data to give you an easy answer, so you let the computer hack through the data and understand what's going on. We're moving from that realm into sort of a limited level of artificial intelligence where you simply throw the data at the machine and let it determine relationships you didn't anticipate first. So essentially you let it ask its own questions. And the programming we're going to be seeing coming forward is going to be about that. And that's very much got to be guided by people understanding what might be interesting to the users.
Absolutely. Yeah, I think that's, you know, that relationship between programming and how it relates to the kinds of tools that are coming is critical. Can we move forward here? We wanted to talk for just a minute or two about training. And as a way of doing that, actually, I put up, we'll go to the next slide, please. This is called the Geospatial Technology Competency Model. This model's been around, oh my gosh, I want to say 15 or at least about 15 years now. This is the way Department of Labor looks at, you know, the education and training that's required for geospatial technologists, basically. And if we can zoom in on it for a second. Next slide. What we can see is that the bottom has these sort of personal effectiveness competencies, and then there's some academic competencies in the foundation, and then workplace competencies. Then you get up into, you know, the industry sector things: positioning, data acquisition, analysis, modeling, software and application, and then kind of application-specific requirements at the occupation-specific things at the top of the pyramid. One of the trends in training, I think now, is project-based learning to try to get people kind of up into the upper parts of this pyramid. And I wonder what your view of that would be, Barry, in terms of a lot of project-based learning approaches.
So I'm of two minds about project-based learning. I think that when you are well along in your practice in the GIS disciplines, that the way you process information tends to be taking sensor source data and inputs from other practitioners and written reports of things that have taken place and maps and clocks and news articles, and you assemble them to make the story map kind of thing Steve was talking about. To do that, however, I think it's very, very critical that you develop a set of reasonable fundamentals in your GIS realm. You need to understand how the tools work well and get practice at using them in fixed drills so that you understand what it is you're doing when you're manipulating them. The learning curve is simply too high if you just start out with projects, in my mind, to do what you need to do. But I do believe that there's sort of the mental graduation exercise in a given area, that once you get to the point of understanding how to apply the tools, then working from the standpoint of, well, how do I apply that to a river flood problem in the Amazon, or a industrial pollution in central China, or communications across the Hutu and Tutsi boundaries at the edge of southern Africa. Those become interesting projects once you have an idea of how to use the tools that are involved. And I think that's the first step that's critical.
Yeah, for the foundational learning is critical. I think we definitely would vote for that. So I think I want to say a huge thank you to Barry for taking time to give us some of his thoughts today as well and engaging in a discussion. It's just fantastic.